Most of us have heard of Sir Isaac Newton. You know, the thing with the apple falling? Well, Newton had, for the longest time, the scientific world in the palm of his hand. His laws of motion and description of gravity led many scientists to begin their research to expand on or improve Newton's law of universal gravitation. Newton's law of universal gravitation sounds like this. All objects attract each other with a force of gravitational attraction. Gravity is universal. The force of gravitational attraction is directly dependent upon the masses of both objects and inversely proportional to the square of the distance that separates their centers. Finally, in 1905, Einstein first published his special theory of relativity, which included his thoughts about the traveling of light and energy through space. Later, he was asked to write many books on his theory. Then he revisited it and made it his general theory of relativity in 1915. The theory is considered to be the last classical field theory, in the sense that classical can mean non-quantum. The difference between his theory and others that came before it is that it treats force by means of geometry, and leads to worries in cosmic phenomena such as black holes, other universes, as well as the possibility of time travel. All other theories regarding force have been referred to under the quantum bracket. The equation for his theory is something you might have seen before, the infamous E = mc squared, or in other words, energy equals mass times the speed of light. Now that you've gotten a little history on the theory, let's talk about what it is so you can correctly understand and identify why it was so important and is considered a turning point in history. Let's use an example from an article talking about this specific topic. In this example, we will be comparing Newtonian physics with general relativity regarding the Earth's orbit around the Sun. So, in Newtonian's law of universal gravity, or NUG, the Earth wants to move in a straight line. The Sun, however, creates a gravitational force field that deflects the Earth and causes it to move in a circular pattern around our star. So, for a visual, if you were to take a ball and throw it in a circular room, the ball would bounce against the walls around the center of that room. But general relativity, GR, suggests that the Sun is bending space-time and causing the Earth to merely ride that bend. It moves inertially in this warped space and in this zone. It follows its new trajectory that has been warped as well into an ellipse pattern around the Sun. To visualize this, imagine you are standing on a trampoline. The trampoline represents space and you represent the Sun. Then, have someone roll a ball onto the trampoline. You will notice that, if your bend is strong enough, the ball will enter the divot you are making and start to orbit around you, such as a planet does in our solar system. You may be shocked to find out that something you use in your everyday life has a comparison to Einstein. Can you guess what it is? Correct, it's your GPS. Einstein's clarifying the origins of gravity and general relativity is responsible for helping you get to where you need to go. But more specifically on the scientific spectrum, general relativity has impacted essentially the whole field of astrophysics. The discovery of black holes, other large anomalies in space, and the idea that massive objects not only bend space, but also the fabric of time. General relativity has influenced many great scientists as well. Scientists such as Edwin Hubble, Alexander Friedmann, and Wendy Friedman are just a few examples of these big-brained individuals. So, an interesting fact about this, Friedmann was working on this equation while Einstein was working on general relativity. It wasn't until after general relativity was published that Friedmann used the framework of the theory to finish his equation nearly 15 years later. The Friedmann equation was published in 1922 by Russian-Soviet physicist and mathematician Alexander Friedmann. In its most convenient form, the equation tells us how to examine the time and temperature for a model of the universe and the Big Bang. Funny enough, Einstein noticed Friedmann's equation and proposed another option that also models the expanding universe. Einstein's revision is known as the cosmological constant. Does this name ring a bell? Well, if you've ever heard of the famous telescope that helps us observe distant galaxies in deep space, then yes, the Hubble telescope was named after Edwin Hubble. But what did Edwin Hubble do to have a telescope named after him? Well, it could be his research and development of deep space telescopes and the fact that he was the first one who found, quote, fuzzy images, end quote, of the first nebulae, or it could have been the fact that he also created, with the help of general relativity, of course, the Hubble constant. The Hubble constant was first thought of in 1920 when scientists used Einstein's equations for general relativity to predict that the universe should be expanding, but they didn't know how. When Hubble graduated college in 1910, he joined this exciting debate. He used his experience with telescopes to measure the brightness of stars to determine their distance from Earth. In his observations, he found that more distant stars seemed to be moving away faster than ones that were closer. In 1929, Hubble and his colleague Milton Humason calculated the mathematical equation to measure the distance to a star and how fast it is moving away from Earth's relative position. This was the first accurate Hubble constant, 500 kilometers per second per megaparsec, or as written out equationally like this. This leads me to my next great scientist. This person is more modern and actually still doing research to this day in the field of quantum mechanics. Wendy Friedman has devoted her career to observing the Hubble constant and fine-tuning it to be as accurate as possible. She continues Hubble's research and observations to this day. In fact, in an interview with Paul Rand, she confirms this. She continues this research and has found a new Hubble constant and was given a Nobel Prize for it at 69.8 kilometers per second per megaparsec, a vast difference from what Hubble thought in 1929. Now, the quantum theory and quantum mechanics is a whole other talk for a different time. However, scientists and other big-brained individuals today are working on combining Einstein's theory of relativity with quantum mechanics. If one were to do this and they succeed in this, they would receive a Nobel Prize and have solved one of the most puzzling scientific conundrums of our time. So, in conclusion, all of that, all those scientists, mathematical equations, terms, discoveries, all of it, gives thanks in some way, shape, or form to Einstein's theory of general relativity. Albert Einstein has paved the way for great scientific discoveries. Some say he was a mad scientist. Some say he was a genius and way ahead of his time. I say he's an innovator.